A relational database looks simple from the outside. You send SQL and rows come back. But inside, it is doing three jobs at once: finding data quickly, letting many users change data safely, and surviving crashes without losing committed work. If you can explain those three jobs, most system design database choices become much less mysterious. The relational model starts with tables, rows, and constraints. Tables give data a shape. Primary keys identify rows. Foreign keys describe relationships. Constraints make invalid states impossible instead of merely unlikely. This is why a database is not just a file format. It is a shared authority over what facts are allowed to exist. A lot of application bugs come from treating these rules as comments in service code instead of constraints in the system that all writers must pass through. When a query arrives, the database does not blindly scan everything. It parses SQL into a tree, estimates possible plans, chooses one, and executes it against pages in memory and on disk. The planner is making a cost bet. Should it scan the table, use an index, join this table first, or hash a smaller input? Good schema design gives the planner better options. Bad statistics, missing indexes, or predicates that hide indexed columns can make the planner choose an expensive path even when the SQL looks innocent. A B-tree index is the classic shortcut. Instead of reading every row, the database walks a balanced tree from root to leaf, finds ordered keys, then follows pointers to table rows. That makes lookup and range queries fast, but indexes are not free. Every insert, update, and delete must also maintain the index, so a write-heavy table with too many indexes pays for them. The practical rule is to index access patterns, not columns in isolation. Equality filters, range filters, joins, and sort orders are what make an index earn its keep. Transactions are the boundary of correctness. Atomicity means all or nothing. Consistency means constraints still hold. Isolation means concurrent transactions behave according to a chosen rule. Durability means once commit succeeds, the database can recover it after a crash. System design questions often hide here. What exactly must be atomic and what can be eventually consistent? If two user actions can break a business rule when they overlap, you have found a transaction boundary, a lock, or a serializable retry loop. Most modern relational databases avoid making every reader wait for every writer. PostgreSQL, for example, uses multi-version concurrency control. An update creates a new row version while old transactions can still see the old version. Each transaction reads a snapshot. This improves concurrency, but it also creates cleanup work and explains why long transactions can hurt a system. The database is carrying multiple histories at once, and vacuum or garbage collection cannot remove old versions while a transaction might still need them. Durability is built around write-ahead logging. Before change data pages have to be written back to their final place, the database appends a compact record of the change to a sequential log and flushes that log. After a crash, it can replay the log and redo committed changes. The key pattern is simple: log intent first, make messy page updates recoverable later. This is also why sequential write throughput, fsync behavior, and checkpoint tuning show up in real database performance. Scaling an RDB is about protecting the source of truth. Read replicas help read traffic. Caches help repeated reads but must be invalidated carefully. Partitioning and sharding reduce hot data per machine but make cross-partition transactions harder. The strong answer in an interview is not to say, use Postgres or shard it. It is to name the consistency boundary first. If an operation must remain atomic, keep it inside one transactional authority for as long as you can. If it can lag, move it to replicas, caches, streams, or asynchronous workers. A relational database is a correctness machine with a query engine attached. Tables and constraints define valid facts. Indexes make reads fast at a right cost. Transactions define atomic change. MVCC lets readers and writers coexist. WAL makes committed work recoverable. Once you see those pieces, database architecture becomes a set of deliberate trade-offs, not a black box. The interview skill is to connect each trade-off to a failure mode. Slow reads, write amplification, stale data, deadlocks, crash recovery, or cross-shard consistency.